Greetings everyone! Today we're diving into a crucial topic: how is global impacting natural disasters and their effects on economy. In this video we will analyze data to uncover a relationship between rising temperatures and the frequency of natural disasters. Additionally, we will explore whether these disasters significantly impact the economy. Without further ado, let's get started.
Firstly, we upload our libraries. We import Pandas, NumPy, Matplotlib, and Seaborn. And then we load our dataset, which is the global temperature data. So, original temperature data equal to pandas.read_CSV, and then we put the location of our data. Then let's create a copy of our data, so our original data will not be affected. Terminus.copy. Now let's check our data. And here we have it. As you can see, we have date time, land average temperature, land average temperature uncertainty, land max temperature uncertainty, land minimum temperature, and the same for uncertainty, land and ocean average temperature, and land and ocean average temperature uncertainty. Now, let's remove the data that are not required for our analysis. Regarding land and ocean average temperature, it gives information about the overall Earth temperature. The global temperature dataset has monthly granularity. As you can see here, we have from 1750 in January, and then in February, and then in March, 1st of April, May, and so on. Now let's choose the required columns for our analysis. So, global temperature data frame equal global temp df. I'll put date time and then land and ocean average temperature. Now let's set the date columns as date time index, and then we sort it. We use pandas dot to underscore date time. Then we use set index sort index. Axis equal to 0 for the rows, in place equal true. Then let's resample annually and rename index and columns. So as you can see, the data is huge. In each year, we have the months. So instead of using the all months in each year, we can take the mean of each year. So resample annually and rename index and columns. Global temperature data frame equal global temperature from the resample and we take the mean. Then global temperature data frame, rename it, rename the columns, in place equal true. And then we take it dot index dot rename, we put the year, and then in place equal true, and then dot index dot year. And finally, let's check the number of missing values. Check missing values. Print dot is null, and then dot sum to count it, and then print also global temperature data frame. We put global temp data frame, put annual average temperature dot is null and dot index. Now let's run our code. Here should be underscore and it's sort and we got the years from 1750 to 1849. So let's try to explain our code. So firstly, global temperature data frame equal to global temperature data frame, and we put the time and land and ocean average temperature. Here, this line filters the data frame global temperature data frame to only include two columns, which are the date and the land and ocean average temperature. And then here we set the date column as date time index, and then we sort it. So we use pandas .to date time. This converts the date column from its original format, likely a string, to a date time object, which allows for easier time-based indexing and manipulation. And then global temperature data frame dot set index, and we put the time in place equal true. Here we set the date as the index of the data frame. This means that when we perform operations on the data frame, it will now use the date as the primary reference for rows. Global temperature dot sort index. Axis equals 0. In place equal true. This sorts the data frame by the index, which is now the date. And for axis equals 0, it refers to operations that are performed row-wise. And then in place equal true, the in place parameter determines whether an operation modifies the original data frame or returns a new one. When in place equal true, the operation will modify the original data frame and return none. And then we resample annually and rename index and column. Regarding global temperature, data frame equal global temperature data frame dot resample a dot mean. For resample a, it specifies that we want to resample the data on an annual basis, where A stands for annual frequency. So instead of having the all months in a year, we just take the mean of all months for each year, one by one. For example, we take the mean of 1750 and then 1751 and so on, instead of taking all months. And then we make renaming for the columns. The columns parameter allows us to specify which columns to rename. Here we provide dictionary where the key is the old name and the value is a new name. And for in place equal true, it modifies the data frame directly without needing to create a new variable for the named data frame. And then global temperature data frame dot index equal to global data frame dot index dot year. This extracts just the year part from the date time index and assign it back to the data frame index. So the result will be, for example, same as we said, 1750, 751, 1850, and so on. Then global temperature diff dot is null dot sum. This line checks for any missing data or none values inside the data frame and summarizes the count of these missing values for each column. Dot is null. This method returns a data frame of the same shape as global temperature data frame, where each entry is true if the corresponding entry in the original data frame is non-missing and false otherwise. Sum is a method to count the number of true values. In this case, it's the missing entries for each column. And now let's try to drop the none values. In our data, the first 100 years from 1750, they don't have temperature values. So we drop those entries to begin the analysis from 1850 onwards. So global temp diff drop nav is drop nav, and then we put in place equal true. In climate science, temperature anomaly represents the temperature pattern accurately than absolute temperature. It is a measure of the departure from baseline temperature. Basically, it indicates how much warmer or cooler it is than the baseline. The baseline used here is the average temperature over the 30-year period, from 1951 to 1980. This is the base period used by NASA. The temperature anomaly values are stored in a new column in the data frame, and the absolute temperature values are dropped. So, let's calculate the global baseline temperature. Calculate the global baseline temperature with global reference temperature equal to global temperature def.log, and we put the year 1951 to 1080, and we're going to take the mean, and regarding the column of average or annual average temperature. Then let's create the temperature anomaly column. Global temperature, def, temperature, anomaly, and we give it the value of global temperature data frame, annual average temperature minus global reference temperature, and then global temperature data frame we drop annual average temperature with axis for 1 is equal to. Then we access the data dot head. Let's run our code, and here we have it. We got temperature anomaly, the year, so instead of months like January, February, March, and so on, we just get the year, and here we got the average or the mean, and the temperature anomaly. So here is minus 43, minus 30, minus 29, and so on. Great. Now let's plot the temperature anomaly. So use plot from Matplotlib, plot figure. We set the fixed size equal to 15 to 8. Plot say global temperature data frame, and I put the temperature anomaly output R. Alright, then the title, plot of title, warming Earth, global temperature, what is well, then 1850 to 2050. Then font size equal, and then we set the X label and Y label. Here, and font size equal 15, and plot.y label. Put it temperature anomaly degree Celsius. Font size equal 15. Finally, plot.show. Let's run our code, and here we have it. We got the warming Earth, global temperature anomalies, annual from 1850 to 2050. As you can see, the y-axis is the temperature anomaly that we extracted from our table that we created here, and the x-axis is the year, starting from 1850 to 2015. And as you can see on the plot, the temperature anomaly is increasing. And as we can see here in 2015, the Earth is about 0.76 degrees Celsius warmer than the normal. The result confirms the scientific consensus that the Earth is warming. Now let's explore the natural disaster data and analyze how the occurrence of the various types of the natural disasters has changed over years. So let's upload our data. Let's put the location of our file. And this is our file. So let's get the location of the file. Copy file. And then natural disaster data frame equal to our data. Copy. I'm not closing our data. And then natural disaster data frame dot hit. So on our code, disaster, and here we have it. Was the entity, code, year, and number of reported natural disasters. So now let's remove the code column here as the values are matched. So disaster data frame dot drop, and I put code, the name for column, and axis equal 1, place equal true. Then check the different types entity values. Dot unique. Here we use unique to check the different types of entities values. So we get the unique values. Let's run our code. And here we have it. These are the types of natural disasters that we have in our data frame. Either we have all natural disasters, or drought, earthquake, extreme temperature, extreme weather, flood, impact, mass movement, volcanic activity, and so on. So the entity column contains 10 types of natural disaster entries and their summation. For further analysis, it's suitable to rearrange the data according to the disaster categories. Now, let's pivot the data frame. So, natural disaster data frame equal to natural disaster data frame dot pivot index equal to year colons equal to entity values equal to number of reported natural disasters. Reported disasters. And then let's look at our data. Natural disaster data frame dot head. Let's run our code. And here we have it. As you can see, we have the entity year from 1900 to 1901 and 2 and so on. Here all natural disasters, and here each disaster alone. Drought, earthquake, extreme temperature, extreme weather, flood, impact, landslide, mass movement, volcanic activity, and wildfire. Global warming doesn't affect the probability of impact by asteroids, meteoroids, etc. on Earth. So the impact entity can be removed from the data frame. We have several nonce values, which could mean missing values or unreported disaster occurrences. So for our analysis, we will replace them with 0, which means no disaster occurrence. And it would also benefit plotting the data. So let's start by removing the impact column, as all values are nonce. So natural disaster data frame.drop impact axis equal 1, which means the column in place equal true. And then let's handle our missing values. So instead of none, we'll make it 0. And put in place equal true as we know. Then natural disaster data frame equal to and disaster data frame dot add underscore suffix, which is occurrence, disaster data frame dot hit. Let's run our code. As you can see, now there is no impact. And regarding landslide, as you can see here, these values were none. Now they are converted to zeros. Now let's plot our data. So let's try to plot the type of natural disaster occurrences from 1950 to 2018. So let's set our colors. Hat disaster the frame drop axis equal 1 dot log from 1950 Let's run our code. And here we have it. Global occurrences of natural disaster for 1950 to 2018. And here, as you can see, we have here the natural disasters like drought, earthquake, and so on. The y-axis indicates the occurrence, and the x-axis indicates the year. The occurrence of floods has significantly increased over years relative to other disasters, and the next highest increase occurrence is the extreme weather, followed by earthquake. So floods, and then the orange, extreme weather, and then the earthquake, or the dark red. So the plot shows that there has been a steady increase in the number of total natural disasters globally. And now, let's try to plot all natural disasters occurrences and the temperature anomaly for comparison. So, Let's run our code. And here we have it, our chart. As you can see, all natural disaster occurrences and temperature anomaly for 1900 to 2015. We can also change the color here. And here we have it. As you can see, the natural disaster occurrences in red color and the temperature anomaly in blue color. So the plot indicates a positive correlation between the temperature anomaly and the occurrence of natural disasters, as both are increasing, especially after around 1940. As you can see here, from 1940 it started becoming warmer than normal. Natural disasters also start rising globally. Now let's investigate the economic damage caused by natural disasters. So let's load our data. We copy the path. Then damage data frame equal to dot p. And then dot. And here we have it. As you can see, all natural disasters, quote the year, total economic damage from natural disasters, and this value is calculated by US dollars. So now let's remove the code column, as all values are man. So x is equal 1 because it's column. Place true. Now let's pivot the data frame. The name of our data frame equal to the frame dot pivot index with year columns entity values equals to total economic damage from natural disasters S $, and then dot head. And here we have it. So as you can see, we have removed the code column. Now there is no code. Now let's remove the irrelevant columns and we rename the other columns and handle the missing values. So fill now to fill the missing values with 0. Dot head dot suffix, and here we have it. And now let's plot the economic damage categorized by type of natural disasters. So plot title economic damage by type of natural disaster for 1915 2018 or silence for good by label economic damage billion US dollars, font size equal 15, .text label here, font size with font team 2, legend of equal 2, third price correction project. And here we have it. We got our plot. Economic damage by type of natural disaster for 1950 to 2018. We have different type of natural disasters, as you can see, Economic damage is highly variable as it depends on several factors, such as the disaster type, disaster location, severity of the disaster, and the disaster management efforts. However, one key trend that stands out from the plot is that the total economic damage from all disasters is generally increasing over years. As you can see, the main reason is an increase in disaster occurrences correlated with global temperature rise, although all disasters do not contribute equally to the economic damage. Another reason for higher economic damage could be the overall increase in economic growth, which leads to more infrastructure, land use, etc. Now let's combine the three main data frames, global temperature, natural disaster, and economic damage, and create a correlation table to measure the correlation between each entity. Join natural disaster data frame, economic damage data frame. And the method how equal to n. Combine data frame dot head. Let's run our code. And here we have it. We got the temperature anomaly or natural disaster occurrences and each natural disaster alone. And those are combined with the year. And the correlation table here, to combined data frame dot core. As you can see, a value of 1 implies perfect positive correlation, and -1 implies perfect negative correlation, and 0 means no correlation between the two entities. Now let's see how temperature anomaly compares to everything. Bind this or, and then we put our temperature anomaly. And here we have it, the all natural disasters and the temperature anomaly. So as you can see here, the drought occurrences is 0.75. This means there is a strong positive correlation between drought and temperature anomaly. This implies the higher temperature anomalies are likely associated with increased frequency of droughts, and so on. And lastly, a better way to visualize the information in the correlation table is through a correlation heat map. So let's plot our heat map. We put our correlation table as the data. Let's see map. Put in the colors. Let's run our code. And here we have it. As you can see, the green color is the highest and the red color is the lowest. The diagonal line here indicates a highly identical relationship between these two natural disasters. So for example here, it's a dark green, which is the maximum value because it unifies the drought occurrences with drought occurrences, and the same for all. Like for example here, earthquake, here it's earthquake too. And that's why this diagonal line is a highly identical correlation between these two natural disasters. But here, for example, the extreme temperature is about 50% correlation with the earthquake. And again, the earthquake has a high probability with the drought occurrences. So in case if we got a drought, there is a potential correlation that we may have also an earthquake.
And here we have reached the end of our analysis. I will leave the links in the description of the video that supported us to do this analysis. Thanks for watching, see you next time.